Good morning, everyone. In this video, we're going to be starting Lesson C on page 6 in the note packets, where we'll be talking about combinations and compositions of functions. Now, composition of functions or composite functions you have seen before in Algebra 2, and you may remember this notation as being read as f of g of x. Say it with me once. F of g of x. F of g of x. It can also be written in this notation with the open circle between f and g, so it's not f times g. That is also read as f of g of x. We can also write composites this way. G of f of x and g of f of x. So composite functions are essentially streamlining two functions together or putting one function into the input of another function. So folks, just to kind of walk you through notation, this says I am putting function g into the input of function f. I am putting g into f, whereas this notation, we're putting f into g and f into g. So you've seen these before in Algebra 2, but what you haven't seen before is some of the more complicated functions we've started looking at with rational functions, and also how we consider the domain of composites. So when we are figuring out the domain, which has kind of been a theme of this unit so far, we have to consider the restrictions of the inner function and the resultant composite function in order to find what our domain restrictions would be. So folks, just to show you why we have to consider it this way, first we're going to start with an example of my favorite composite function. So if I streamline this f function with this g function, this is what we would get for our composite. So my f function is a hand mixer function. We put ingredients in, we use our mixer function and we blend them together and we get batter. Now, if that output becomes the input of another function, so if f of x, the batter, now becomes our x input of our oven function, if we put that batter into our oven function, we get an output of a cake. So if I find g of f of x, or if I put my f function's output into the g function, so I'm taking that batter and putting it into the g function, then we would get a cake. Now, if we streamline going in the other direction, so if I take my cake out of the oven and put my hand mixer down into the cake, if you put a hand mixer into a cake, are you going to get the same ingredients you started with? No, you're going to get a big old crumbly mess. So f of g of x yields something different than, g of f of x yields something different than f of g of x. So depending on the order I'm streamlining the functions together, that's going to give me a different equation and can thus lead to different restrictions on our domain. So folks, to explain the domain restrictions, I want you to consider, I better zoom out a little bit. I want you to consider these two functions. I've got the microwave function, which has a restriction that you cannot put foil in the microwave. So I don't know if you guys know this, but hopefully I have saved you from a microwave explosion if you did not know this. So we can't put foil in the microwave. Now the freezer, you can ignore this, we're just gonna consider that the freezer basically has no restriction. So I can kind of put whatever into the freezer. Now if I streamline these two functions together, I put something in the microwave and then I take it out and put it in the freezer, what we're going to find is that even though I can put whatever I want in the freezer, because I'm going to be microwaving it first, when I streamline my microwave freezer functions together, that composite, g of f of x, also has the restriction that we can't put foil in there. So even though my freezer has no restrictions, because I'm putting stuff in the microwave first, I have to consider any restrictions that I have there. So how this is going to relate to some of the function stuff we'll be doing is if I think of a square root function and I think of a linear function, y equals x, I don't have any restrictions to the domain of a linear function. The domain is all real numbers. I can literally plug whatever I want in for x. Actually, let's go ahead and make this x squared. So quadratics also has a domain of all real numbers. So I can plug whatever I want in for x squared. But for square roots, I am restricted. It's not that I can't plug in FOIL, but we can't plug in any negative numbers. So this has a restriction that my x values need to be greater than or equal to 0. So when I streamline these two functions together or plug this function into the other function, this restriction goes with it into the composite. So even though this larger function has no restrictions, I still have restrictions on the original input or the original function. So we'll come back to this example in just a moment after we start diving into some of these problems. So folks, we're going to start with this first problem where I have two functions. I've got f of x, which is my linear function. And how many restrictions does f of x have on its domain? It doesn't have any restrictions. No restrictions because the domain is all real numbers. Now, if I look at my g function, does this function have any restrictions? Yes. Remember, anytime I have a denominator with a variable in it, there's always going to be something that makes this dividing by 0. So looking at that denominator, the restriction I have is that x cannot be equal to -2. So that's my foil in the microwave that would make this function undefined. So that is a restriction. So folks, let's go ahead and algebraically find f of g of x, which says we're going to take our g function and streamline it with our f function. So we're going to start with x, plug it into our g function to find g of x. G of x becomes the input of my f function, so I'm essentially plugging g of x into f of x. So g of x here is my inner function. So folks, let's go ahead and see what this looks like notation-wise. How I like to do these problems is I like to start with the shell of the f function. So my f function is 3 times an input plus 7. So just in generically speaking, f of something is 3 times something plus 7, or f of an input is 3 times that input plus 7. So if I wanted to find f of 4, we would plug 4 in for x and put 4 in that parentheses. F of -2, plug -2 in for that input. But I want to find f of g of x, not f of 2 or f of -3. So if I want to find f of g of x, what I'm going to put in for input is the entire g function. So 4 divided by x plus 2. So I'm taking my whole g function and plugging it into the input of my f function. So this is how the label works. This is how the work looks. So how can I simplify this? Well, 3 times 4, and we can write this as 3 over 1. We multiply straight across when we're multiplying fractions, and this gives me 12 over x plus 2 plus 7. Now, if I wanted to simplify this a little bit further and write these as one fraction, we could multiply the 7 by a creative form of 1, or by the denominator over the denominator, so that I can get these to have a common denominator so that I can add them together. So multiplying by that creative form of 1, we get 12 over x plus 2 plus 7x plus 14 over x plus 2. So remember, if I have a half of a pizza plus a half of a pizza, we add the tops and keep the denominator the same to give me 2 over 2. So in the same sense, I'm going to add my tops, which will give me 7x plus 26 all over the common denominator of x plus 2. All right, folks, so what is this equal to? F of g of x. And folks, on the homework over this, I want you to include that label with your answer, because it's not enough just to find the composites. We need to know which composite we found. Did we find f of g of x or g of f of x? So that is what f of g of x is equal to. All right, folks, so algebraically, again, that should be a review of what you've done already in Algebra 2. But now we are ready to consider the domain. for the domain, we have to consider the restrictions of the inner function and the resultant composite function. So let's go ahead and look at who our inner function is on this one. Our inner function is g of x. So my inner restrictions are that x cannot be equal to 2. So just like when I streamline the microwave to the freezer function, if it can't be equal to FOIL in the microwave, if we streamline those two functions together and put the microwave inside the freezer, we're not going to be able to have that FOIL as well. So my inner restriction is that x cannot be equal to -2. But then I have to consider the composite restriction as well. So folks, when I look at my simplified composite expression, does this function have any restrictions? Unfortunately, it does. Because there's a denominator, we automatically know there's going to be some x value that makes dividing by 0 not okay. So what x value is not going to be okay? Oh, -2. So it's actually, luckily, the same restriction as our inner function. So that means my domain is all real numbers except for -2. So my domain will be -infinity to -2, parenthesis, union -2 to infinity. So actually, folks, I'm going to make this a different color to show you that this -2 we determined from both of these restrictions. So this is what led me to that. Congratulations, we have now done our first composite function with our first new domain. So let's go ahead and move to streamlining in the other direction. What happens when I put the f function into my g function? So again, folks, g of 4, we'd plug in 4 for x. G of 5, we'd plug in 5 for x. G of f of x, we're going to plug our f function into our g function. So 4 over an input plus 2. So that's the shell of my function. What am I going to put in for that input slot where my x is? We're going to put in our f function. So 3x plus 7. So I don't really need those parentheses, and I can just simplify that denominator, which will give me 4 over 3x plus 9. Now, this is simplified, but remember that to find denominator restrictions, it is easier if it is factored. If you're looking at that going, well, can we actually factor it? Always check for a GCF first. If I take out that 3, that leaves me with x plus 3, and this just makes it a little bit more obvious that we will have a restriction of -3 here. So this is what g of f of x is equal to. And again, folks, I tend to use the parenthetical notation, but my math lab and your homework will use a combination of both so that you can get used to both notations. So math teachers always joke and say the fog and Goff notation, but they're still read as f of g of x and g of f of x. All right, folks, so that is my composite equation. So notice streamlining this way looks different than streamlining this way. Just like if I streamline my mixer function to my oven function, we get a cake. If I streamline oven to hand mixer, we get something different. So usually your composites will give you 2 different answers. We'll get to the reasons when they don't a little bit later. So folks, to find our domain, we now need to consider my inner function restrictions and my final composite restrictions. So who's my inner function in this one? My inner function is f of x. And f of x doesn't have any restrictions. So my inner function has no restrictions. But what about my final composite? My composite has a restriction that x cannot be equal to -3. So this is kind of interesting because there were no restrictions on my f function, and the restriction that I get from my composite is different from my g function. So by streamlining these two functions together, and again, I can't think of a great example of when this would happen, like using a freezer or in a microwave, but we actually create a new restriction based on how my numbers simplified. So now, considering only these restrictions, what will the domain of my composite be? Well, it's all real numbers except for -3. So negative infinity to -3, union -3 to infinity. And again, it's kind of weird, folks, because even though my g function has that x cannot be equal to -2 restriction, that has no effect on the domain of the composite. So putting that f of x function and streamlining it to my g function, it actually gets rid of that x cannot be equal to -2 restriction. All right, folks, so now we are going to see what happens if we wanted to find g of f of 2. So if I wanted to streamline it like I showed on the previous papers, what we could do is say x to f of x, input to output, and then this becomes my x for my g function and g of x. All right, folks, so 2 is my input. What's f of 2? Well, f of 2 is going to be equal to 3 times 2 is 6, plus 7 is 13. Then if I take that 13 and plug it in for my input of my g function, 13 on the bottom plus 2 gives me 15, and 4 divided by 15 is 4/15. So 13 is this input, and 4/15 as my output. So g of 4/15, or sorry, g of 13 is what gives me the 4/15. So folks, this is just showing what streamlining these two functions looks like. But as you can see, doing it this way is kind of annoying. I take an input, I get an output, that output becomes my input, and then my input becomes another output. So what's nice about this is we have an equation that represents the composite. So I can just take that 2 and plug it in as an input into this equation. So g of f of 2 would be equal to 4 over 3 times 2 plus 3, which gives us 4 over 3 times 5, which is 4/15. So we get the exact same thing. Now, the other nice thing about having our equation for the composite, that g of f of 2 or g of f of x, is we can take a look at that x value and see if it's even worth our time plugging it into that equation. Like, is that x value going to actually exist on my function? If I look at that input or that x value, is 2 on my composite's domain? Yes. 2 is between -3 and infinity, so it is in the domain. So it does make sense to plug that into our function. All right, folks, in the next video, we'll be moving on to the problem at the bottom of page 6.